welcome everyone. We're very happy this week to have Mark Haskins from Duke University, and he's going to talk to us about solitons in Bryant's G2-Laplacian flow. Go ahead.
Right, thanks, Vera. Thanks very much. Thanks for everyone for joining virtually. So I'm going to give a sort of overview of some recent work, somewhat still in progress, with Johannes Nordström at Bath, and also a summer undergraduate research student, Rowan Juneman. So I'm going to explain what Bryant's G2-Laplacian flow is, and I won't say too much about exactly what is known from an analytic point of view there, and I want to instead focus just on some particular solitons that we've been studying recently. So many of you will probably know a lot more about geometric flows than I will, and for Laplacian flow, then this is something that Vera has been thinking about an awful lot longer than me. So let's just give some sort of preliminaries to set things up. So, so we want to just say a little bit about G2 and what it's got to do with three forms in 7 dimensions. So all the way back prior to the classification of complex simple Lie groups or Lie algebras, then when Killing was trying to classify them, originally he thought there were only the sort of classical Lie algebras. But Engel thought that in fact there ought to be a way to construct a 14-dimensional simple Lie group by taking a generic 3 form in 7 variables. So this turned out to be the case, but somehow the picture wasn't completely settled until nearly 30 years later. So what do we mean by a generic K form? Let's talk about complex K form. So if we've got a K form, then obviously we can pull it back by any general linear group element. And so generic just means that its orbit under the general linear group is open in the space of all K forms. So for any K form, if I look at its isotropy subgroup, the stabilizer of that form, so the general linear elements that stabilize that, then clearly to be a generic 3 form, what I need is that the dimension of GL minus this should be the dimension of the space of all K forms. And in general, as we make the dimension too large, there will be no way for this to be true. But if we're in the special case of 3 and 7, then this is 49, this is 35, the difference is 14, which is indeed this dimension of G2, so this is at least plausible. So, so Engel in 1900 started off really by looking at the case of complex generic 3 forms and the orbit under GL 7c. And it's simpler in that case in that every generic 3 form has isotropy group isomorphic to this complex Lie algebra G2. We're going to be interested in the real version of this, in which case things are a little bit more subtle. So over the reals, then this was a student of Engel called Ricci, who seems to have disappeared more or less after this. So if now you look at real 3 forms under the real general linear group, then it turns out actually that there are 2 types of generic orbits. And those will correspond to the fact that this complex Lie algebra has two different real forms, one of which will be compact, the other one is non-compact. So we'll be interested in the compact one. In that case, then it leaves invariant a positive definite symmetric bilinear form. And then the stabilizer of that, a form in that orbit, is isomorphic to this compact simple Lie group, whereas the other real form is compatible with a bilinear form, a definite non-degenerate bilinear form, but of signature 4-3. So we'll ignore that for today. So we'll be interested in a generic real 3 form that is one of the positive ones. So the induced non-degenerate bilinear form is positive definite. And we'll call that a positive 3 form. And this open orbit we'll call the positive 3 form. So sometimes it's the case that generic things, it's hard to describe a particular element in it. In this case, that's not the case. So using octonionic multiplication, one can easily exhibit a particular 3 form. So if you're used to thinking about the quaternion and geometry in R3, the cross product by taking the imaginary quaternions and taking multiplication, you can do the same thing on the octonions. So if I view R7 as the imaginary octonions, then I can define a vector cross product on it by taking my 2 imaginary octonions, multiplying them together as octonions, and then taking their imaginary part. But since the octonions are also a norm division algebra, then out of the norm I polarize and get the inner product. And so I can also form a 3 form by 0 by taking the cross product of 2 elements and then its inner product with a 3rd one. So that gives me a 3 form constructed out of the cross product and the metric. And then this 3 form is such a positive 3 form. And so clearly this way, if I take something that's a automorphism of the octonions, then it's clearly going to preserve this and also this cross product. So I'm going to definitely have anything that preserves in this stabilizes phi, but in fact also the reverse is true. So anything that just preserves the 3 form must preserve the whole structure of being an automorphism of the octonion. Okay, so that was just a very quick review about where G2 and 3 forms come in and what the link to sort of special properties of dimension 8 and the octonions are. So if we want to do what are the special structures on 7 manifolds that arise because of the presence of this group P2, then the simplest thing is just to insist that you have this structure at every point. So, so if phi 0 is my particular choice of 3 form constructed via the octonion, then at a given, on a smooth manifold, then I can ask that there be some isomorphism from the tangent space at that point to R7 that pulls back my standard model and gives me some given 3 form at the point. So, so this is just a point-wide thing, and I want to insist that my 7 manifold be oriented and that this phi be an orientation preserving that. So then out of this point-wise construction, I just make a bundle out of that whose fiber is that point, and then a positive 3 form is just a section of that bundle. So just 3 form that lives in that at every point. So every time I have a positive 3 form on M, then it does give me a reduction of the frame bundle to some principal frame bundle, principal sub-bundle of the frame bundle with fiber G2. So it gives me a G2 structure in the usual sense. And we've chosen a given orientation on M, and it's compatible with that orientation. So these positive 3 forms are basically in one-to-one correspondence with oriented G2 structures. So, but this is not very interesting from a geometric point of view. It's purely a topological question that you have a positive 3 form on your 7 manifold if and only if your 7 manifold is orientable and thinable. So, so if you want to get some more interesting geometry, then you want to put more conditions on your structure. And you know, there are rare things that you can do, but the most sort of the strongest condition is to look at manifolds with holonomy group G2. So let me just say a little bit about that. So it's well known since the mid-50s that the possible holonomy groups of Riemannian manifolds in a sort of generic case. So you want to look at things that are not locally symmetric spaces where you have far fewer constraints because the whole parallel or whole curvature tensor is parallel there. You want to get rid of things that are reducible, and if you want to make things nice, be able to make global statements easier to assume since it's connected. So in those, under that setting, under that assumptions, then Berger showed that the possible holonomy groups of Riemannian manifolds are extremely limited. So there are 5 possible infinite families plus 2 exceptional cases. And then the 2 exceptional cases occur in dimension 7 and 8, and G2 occurs in dimension 7, and spin 7, the double cover of, sorry, 8 appears here. So, so if we take these exceptional cases plus, well, so in these 5 infinite families, then 2 of those infinite families are just holonomy SON and holonomy UN. So those correspond to generic Riemannian manifolds and generic Taylor manifolds. So if you take these 2 plus the 3 families there, those constitute what we call the special holonomy metric. And then all the special holonomy metrics are necessarily Einstein. And in fact, except in one case, they're all Ricci flat. So in particular, the exceptional holonomy ones are all Ricci flat. So Berger does not say that all of these things have to arise. He just says those are the only things that can arise. And so knowing that they're Einstein or Ricci flat obviously tells you that proving existence of these is actually highly non-trivial. So proving the existence of all the possible families of special holonomy metrics in various levels of generality, either sort of as a local construction or complete metrics on non-compact spaces or on compact spaces, took most of the 40 years from mid-50s to the mid-90s and involved some rather deep developments in geometry and analysis. Most famously, probably Yale's proof, the Calabi conjecture, settled the cases where the holonomy is the group, a special unitary group, or this compact fermion group. And in that case, you can reduce to, by working in a given Taylor class and using the DD bar lemma, you can reduce to a scalar equation, but you end up with a fully nonlinear scalar elliptic equation, a complex Monge-Ampere equation, and then Yao solved this by the continuity method. In the exceptional holonomy cases, then there is no known way to reduce to a scalar equation like this. And rather, the best that's sort of known is a system of nonlinear first order PDEs. So I'll just say something very briefly about what happens in the G2 case. So it's not, at the beginning, it's not obvious that holonomy leads to PDEs at all, in the sense that holonomy is a integro differential condition. But the way to think about it is partly via thinking of the three form rather than working with the metric directly. So when I think about the holonomy group of a Riemannian manifold, then the main thing that the holonomy does is determine exactly what the parallel tensors are on my Riemannian manifold. In particular, if I have holonomy inside of G2, then this kind of three form that I have, which is invariant under G2 by its definition, will get turned into a parallel positive three form. Okay? So if I have a G2 holonomy metric, then I'll have a positive three form, but it will actually be parallel. So if I start with a G2 structure, then I've got an induced metric because G2 is a subgroup of SO7, but then I want to just write out the condition that that induced metric be holonomy contained in G2. Well, we know it must be parallel, so so if the holonomy is contained in G2, then there must be, if it's parallel, then it certainly must be closed and co-closed. But also the reverse is true, that it's sufficient to know that the form be closed and co-closed, and then that actually says there must be a parallel form, and therefore the holonomy must reduce to a subgroup of G2. So it doesn't say the holonomy is exactly G2, but we've got now at least some differential conditions rather than integro differential conditions, and then we've got a containment of the holonomy. So let's think about the equations occurring here a little bit more. So recall that in order to define Hodge star, we needed a metric, but the way that the three form determines a metric is nonlinear, sort of cubic in the three form. So in this statement here, then this operator depends in a nonlinear way on the background three form that we have. So we've got this equation genuinely is linear in phi, but this one is not. So in any case, we call something that satisfies this condition here a torsion-free G2 structure. So you can talk about torsion of a G2 or a G structure, and this is equivalent to that intrinsic torsion. So, so rather than concentrating on the metric, we've concentrated on the three form, and we've looked at the condition to be a subgroup, the holonomy a subgroup of G2, and we've got differential equations. So how many equations did we get? So this was a three form, so it depended on 35 coefficients. We've got a vanishing of a four form and the vanishing of a five form. So it's also like a three form and a two form. So that gives us 35 conditions and 21 conditions. But it turns out they overlap by 7. And so what we end up is 49 equations for these 35 coefficients. So we get a first order system of 49 equations on 35 unknowns. So still, it's not the sort of thing that your typical analyst would like to study. And the first approach to try to think about it would be you've got apparently an overdetermined system, so you would use methods designed to solve overdetermined equations, and that's exactly what Robert Bryant did using the methods of exterior differential systems. But there are also some elliptic methods that you can use to study this, but essentially only perturbatively. So all of the current flavor of results are, suppose that you can in some way get your hands on a G2 structure which satisfies d star d of phi is 0, so we'll call that a closed G2 structure. And then its failure to be torsion-free is now measured by d star phi. So then if you can make something where d star phi is sufficiently small, then there's a general fairly robust perturbation theory developed by Dominic Joyce that says you can correct that to something with exactly torsion-free. And so then the art form is trying to find closed G2 structures with small torsion in creative ways. So by now there are a number of different ways to do that. So Joyce's original Como constructions, variants on that using QALE spaces, then the twisted connect sum construction that was suggested by Donaldson, first investigated by Kovalev, and then in some more detail by myself and collaborators, and then more recently Dominic and Spiro have gone back and sort of generalized quite a bit of what Dominic did, where you can replace objects that used to had to be assumed to be flat to be more curved, but then it's difficult to find too many examples of this. But, there's a lot of potential for extending that construction. So what I want to talk about today, so that's more or less all known constructions of compact G2 holonomy manifolds are via that perturbation theory. But
so Mark, may I ask for this? For this gluing thing, I mean, I thought one uses the implicit function theorem, so why doesn't this contradict the counting? Why is the gluing construction not an overdetermined problem?
Well, so first of all, I haven't here really taken into account any diffeomorphism invariance. And so this is a bit of a fictitious count here.
Okay.
So I could try to think of it, I could try to think of the problem locally, and then my form would be exact and everything would change, but I mean, the basic picture is that by the time you impose the diffeomorphism invariance, then suppose that you had a G2 holonomy metric and you look at what nearby ones would be like, then they would be given by the harmonic 3 forms on your manifold. So you would have a moduli space of them. And in that, unlike for a general Ricci flat space, then in that case, you could actually prove that that's the smooth point of the moduli space. And so now the general sort of perturbation theory instead is you're not quite at that situation and you want to understand, you know, what has kind of changed, you know, how, yeah, I mean, without going into a bit of G2 representation theory to say three forms should split this way, and it's a little bit difficult to be too specific.
Okay, thank you.
But I mean, just because, and it doesn't mean that all of these equations are really independent. I mean, it's just a crude parameter count is the first thing. It doesn't include diffeomorphism invariance in the second one. And you know, whenever you have an overdetermined system, there still could be more solutions than you expect. And that's exactly what, you know, Robert Carton-Taylor sort of thing will tell you is, you know, for an overdetermined system locally, how many functions of how many variables does a solution depend on? So I'm not sure I've done a very good job of answering the question.
Maybe I can just add for Bob that there's what Dominic did for his existence theorem. There's a way to gauge fix somehow, get rid of the diffeomorphism invariance, and then you really do get Laplacian of some two form equals some nonlinear quadratic stuff in first derivatives. So it really becomes, if you do it the right way, it does become an elliptic equation. It's hard to see, right? Definitely.
But only for, you know, only for somehow things close to, that were already close to something that was a solution.
Okay.
But in any case, today I want to essentially ignore, I mean, I want to say as far as actual construction to date of G2 holonomy manifolds, everything has been done this way. But now I only want to now talk about parabolic related things, which, you know, so far has been, you know, not a good way to construct G2 holonomy metrics yet, but which I think at least is gives rise to a collection of interesting analytic geometric problems, and maybe one day far in the future will be useful. So there are a number of different flows of three forms that one could introduce, and there are a few survey articles that came out of talks given at the Fields Institute a few years ago. I'm going to concentrate on what I would regard as the most geometrically natural one, which is something that works on closed G2 structures. So there's a very natural flow introduced by Robert Bryant, which is that for a given closed positive three form, then you try to solve the following problem, that you try to say that the time derivative is the Hodge-Laplacian of your initial three form. So it turns out that you know, this closed condition is satisfied once it's satisfied at time 0, it's satisfied for all t in the lifetime. And as a sign that you're not doing something completely crazy, then if you, so every phi t gives you an induced metric G2. If you look at how the metric evolves, then it evolves via Ricci flow up to terms that are quadratic in the, if this thing does not have zero torsion, then this thing is quadratic terms in that torsion. So clearly, if I take something that's closed and co-closed, then this Hodge-Laplacian term vanishes. And so, in fact, the stationary points are exactly the torsion-free G2 structures. But more than that, the Laplacian flow actually has a gradient flow structure. So Hitchin introduced his so-called volume functional. So given a form phi, we have its induced metric g phi. Therefore, I can also talk about Hodge Laplacian, and I mean Hodge star, and therefore I can take phi wedge star phi, and on a compact manifold, I can then integrate that. Then I can, given some initial phi 0, I look at the, I fix that given cohomology class and now vary the volume functional restricted to that class. Then what Hitchin showed is that the critical points of volume are exactly the torsion-free G2 structures. They're all maxima, or the second variation is greater or equal to 0, and I mean less than or equal to 0. And the only 0 directions are the presence of diffeos. So, but this is actually a sort of upward gradient flow for the Hitchin volume. So that means, for instance, that when you look at how the volume increases, how the volume changes along the Laplacian flow, then it's strictly increasing along the flow. Okay. So a natural question would be, does this flow have short time uniqueness and existence? And the answer is yes. It's not completely trivial. So that was proven in an unpublished paper of Bryant and Zhu. The subtlety is that even once you take into account diffeo invariance, then essentially what you get is things are parabolic only in the direction of closed forms. But you can either then directly do the Nash-Moser, or it was pointed out recently that in Hamilton's 1982 JDG paper, then he gives a general setup which allows the integrability condition to be imposed, and if you appeal to that, then that fits within that class of problems that Hamilton considered. So uniqueness and local uniqueness and short-time existence and uniqueness is true, but not completely trivial. A number of things have been done since. I mean, in no way does the state of development of Laplacian flow at all resemble the state of development of mean curvature flow or Ricci flow or Yamabe flow. But the last few years have seen some improvements, and for instance, there is a sort of stability result due to Lotay and Way, so that if you start sufficiently close to torsion-free G2 structure and let it flow in the Laplacian flow, you will come back to a torsion-free G2 structure. Although the proof is not completely sort of self-contained in the sense that you somehow need to use some of the elliptic perturbation theory in order to prove that. So from a purely parabolic point of view, it's not very satisfactory. But anyway, I think it's fair to say that, as in most geometric flows in higher dimensions, we're not expecting that in general the solution should run for infinite time and always converge. We're definitely expecting that there should be some sort of singularities, but at the moment we don't really have a clear idea of what those singularities are. And so the work here is an attempt to suggest some sort of singularities that one should definitely start thinking about. So in most geometric flows, then the simplest models for singularity formation have come from solitons in the flow. So in the context of Laplacian flow, then what we mean by a soliton is that we've got some G2 structure, a vector field, and some scalar. We want the G2 structure to be closed. Then the sort of equation that we want is that now the Hodge Laplacian should be lambda times phi plus the Lie derivative term. And so, as usual, those correspond to self-similar solutions of Laplacian flow, where my form can get pulled back by diffeo f together with dilated or expanded by this scale factor. So the diffeo is generated by this vector field that again is distorted by this scale factor, which depends on the sign of lambda. And so with these sign conventions, then lambda, so this kappa is growing when lambda is positive. So these correspond to expanders. So in particular, they will give rise to immortal solutions, so solutions that exist from some time up to infinite time, or steady solitons, so things that exist for all time, or negative shrinkers for ancient solutions that start at backwards minus infinity but stop at some time. Okay. So just some obvious things to notice here. So the first thing to notice here is that this term, we're saying this is closed. So by the Cartan formula, we've got two terms, one of which disappears. And so this term is exact. Also, one of these terms disappears, so this is also exact. So if lambda is not 0, then this 3 form is exact. So a non-steady soliton, this 3 form must be exact. So now also, if you just think about the behavior of volume, that volume is increasing along the flow, and that certainly means that you can't have any shrinkers. And in fact, any steady one on a compact manifold must actually be stationary, must be a torsion-free solution. One cannot rule out expanders, but at the moment, no compact expanders are known. And it's a non-trivial question to answer because, again, the symmetry group so you would have no continuous symmetries for these expanders. So,
Mark, can I ask a question?
Yeah.
So whether or not there are any expanders that exist in the compact case, we haven't shown yet whether solitons are directly connected to singularity formation in this flow, have we?
No.
Okay, so even if one proves that there are no non-stationary solitons, that doesn't mean there are no singularities.
No, I mean, in some sense, all of those, immortal, eternal, and ancient are in some sense more natural just from the point of view of what are you going to obtain by a blow-up procedure. Typically there's some other blowdown procedures that, in one of these other situations would also associate to them some soliton at infinity that may be kind of degenerate. So, but no, a number of basic things that are known in mean curvature flow and Ricci flow are still unknown in Laplacian flow. So, yeah. And then, as usual, then there's a scaling behavior that if I want to change the value of lambda, then I can do that by the appropriate scaling of other geometric quantities. So in particular, if I've got some original free-form in X, which is a lambda soliton, and I want to make it a k over 2, lambda k over k to the 2, then I have to scale the free-form of the vector field like this. So this is important later on, mainly just as a difference between the steady case and the other cases, namely that rescaling a steady soliton gives me back another steady soliton, but otherwise changes the value of the parameter. Okay. So as I said, and as Bureau pointed out, then we don't know the extent to which a singularity model in Laplacian flow is necessarily modeled in any sense by a soliton. So, but that has been the case, at least sort of morally, in most other flows that one has come across. So, so it makes sense to start looking for solitons as potential models for singularity flow. But already, if I put lambda 0 and don't have a vector field, then this is just giving me back a torsion-free G2 structure. So this is something sort of potentially more exotic than this. So I certainly don't have too many methods for constructing those things. Pretty much the only things I could do would be try to do some kind of perturbation theory, but then I've got to start with something that's a reasonable almost solution, or otherwise I could look for things that have symmetry. And that's also the case to a large extent in Ricci flow, unless you're in the Kähler-Ricci flow context, in which, again, you have some complex Mongean pair going on. So in some sense, what we're going to look at is solitons in the Laplacian flow that have a reasonable but not kind of maximal symmetry. So maximal symmetry would be to ask that these things are homogeneous. And there is a literature on that, and but I see that as maybe more relevant to understanding what might happen to Laplacian flow for t going to infinity, when maybe in the same way that in Ricci flow, when you want to see what happens once you've done your sort of connect some decomposition, and towards infinity you want to see a thick thin decomposition and see some of the certain geometries appearing with some collapsing, then this is maybe more relevant here. But I want to instead look at things where there's a group of symmetries acting with codimension 1, and that I'm particularly interested in things that are shrinkers. So if they're shrinkers, we already know they must be non-compact. And I would like to look at shrinkers that are asymptotically conical. So we also knew that if they're not steady, then they have to be exact. So if you start thinking about known G2 holonomy metrics that are asymptotically conical, but now want to imagine deforming them a little bit, then there's one on the spinor bundle of S3, but that has a associative compact 3 cycle, so that's definitely not exact. But there are two other well-known solutions in the torsion-free case due to Bryant and Salomon on lambda 2 plus or minus of CP2. It just depends on what orientation you give your CP2, whether you call that plus or minus, or on the same thing on the force field. So both of those have a lot of symmetry, SU3 in the CP2 case or ST2 in this case. So, so our goal is to try to find solitons with this symmetry on this topology. So this is a rank 3 bundle over CP2 and a rank 3 bundle over S4 with a certain symmetry. And in some sense, we can find things that are deforming away from a torsion free. So let me state what the three main results are and then try to explain what goes into proving them. So the first theorem is that if we look at steady solitons, then on CP2, on lambda 2 plus of CP2, but not on lambda 2 plus of S4, then there is a one parameter family of steady solitons asymptotic with a particular rate, all asymptotic to the torsion-free G2 cone that appears in the Bryant-Salomon metric. So these are steady, non-torsion-free things that are asymptotic to a torsion-free cone at infinity.
So Mark, can I ask a question?
Yeah.
So the Bryant-Salomon metric itself is not in this family. You said none of these are torsion-free.
So the Bryant-Salomon one appears as a sort of degenerate limit of this family.
Because that one is rate -4, but somehow the rate gets much better in that limit. So this -1 is
Much
sort of,
worse than this, it's.
so the -1 is definitely, it's not that, it's no worse than -1. It actually is -1.
Yeah.
I see.
I mean, this means it's decaying much slower to the cone.
Yeah.
Yeah. So, so I find this interesting in that, but certainly steady solitons in Ricci flow and Kähler-Ricci flow have been fairly well studied. And for instance, in Ricci flow, then there's Bryant steady soliton that's FON invariant. And a lot is now known about this thanks to work of Brendel and others. But that has a kind of paraboloid geometry at infinity. So it certainly doesn't have this maximal volume growth. In Kähler-Ricci flow, then there's an example, a very symmetric example due to Widong-Tao, and then sort of you can take quotients of that and resolve to get lots more, or there's a more recent analytic construction of Ronan Conlon and Alex Steriwal. But in that case, the volume growth is sort of half the dimension of the manifold in question. And so it's not clear, or it's clear that these steady solitons with submaximal volume growth don't play sort of an interesting role in singularity formation in finite time in Kähler-Ricci flow. So the fact that there are AC steady solitons that deform away from a torsion-free thing is I think, an interesting feature of the Laplacian flow that makes it look a bit different from Ricci and Kähler-Ricci flow. So second theorem is there's an explicit AC shrinker on both of these spaces with a particular rate, -2. So, shrinkers are, relatively rare, and they're the typical way that you would think of modeling the formation of, in this case, the conical singularity. So, and then the third theorem says that, again, both on both of these spaces, then there is at least a one parameter family of complete expanders on them. And in fact, conjecturally on the second one, then there should actually be a two parameter family of complete expanders. So this is sort of the simplest way in which you could, again, model Laplacian flow, smoothing out certain sorts of conical singularity, at least for a short time. Okay, so that's the result that I'm wanting to describe in a little bit more detail. So before I do that, I just wanted to ask, are there any questions just about the rough statements of the main results? Okay, so
I have a question. So
yeah,
when you say in theorem B it's explicit, you mean you actually solve exactly the equations?
yeah.
So can you actually? So it's exact. No, it's not exact here. Can you actually say what the torsion is in that case, since it's explicit?
Yeah.
Are you going to tell us, or?
It's
okay. I'll wait. It's fine.
Yeah, I'm going to write down the solution.
Okay, good. Yeah, thanks.
So all right. So let's just do a little bit just about ST3 invariant G2 structures away from. So take out the zero section of this rank 3 bundle, and now then that space is just R plus times the cross section, and then depending on whether M is CP2 or S4, then that's the fixed manifold, the flag manifold F12, so SG3 mod P2 or CP3. And then in this case, there's an action of the obvious action of SG3. In this case, there's an action of FP2. And then it turns out when I look at invariant 2 forms on this one, then there's a 3-dimensional space of those, which are labeled omega 1, omega 2, omega 3. And then there are 2 invariant 3 forms, but only one of them is relevant in our case. This, we'll call it alpha. And then our closed invariant 3 form, our closed invariant G2 structure should take this kind of form. So I've got 3 non-negative functions or positive functions. So my 3 form has this sort of form that it's the sum of fi omega I, fi squared omega I, wedge dt, where t is arc length coordinate sort of perpendicular to the orbit. And then there's this final term, the product of the FIs. And asking that this be closed, just knowing what the structure equations are for these just tells you this one equation here. If you think about what that says using this sort of, here's a geometric mean and here's a sort of quadratic mean type thing. If you figure out what that says, it says that this derivative is at least a half. So this is controlling the volume growth. So if this thing ever is complete, then the volume must be growing at least like t to the 7th. So you can't have something collapse. Okay. So then this is the case of FQ3. You can regard the CP2 case as sort of subcase, as Clayton and Swan sort of realized that basically in that case, there are only two forms, which is basically a kind of combination of those two forms, these two forms here. And so what you can end up doing is if you set F2 equals F3 here, and then apply everything else, then you can regard the SP2 invariant case as a subcase of this one. So, but it has some extra from seeing the sort of general structure, then it's better to think about the SU3 invariant case, but for being able to get some global control of things, in the end, it's sometimes convenient to restrict to the SP2 case. So one way you might think about trying to obtain a soliton would be to say, well, suppose that I start with a cone, then what is my flow going to do to that cone? Is it going to smooth it out into something nicer locally? And for instance, that's sort of what happens in, you take a rotationally invariant metric, change the cone angle, and the Bryant soliton, SO and invariant solitons are obtained this way. So you could do the same kind of thing in this case, but you have to start with a closed G2 cone. Otherwise, it's not even permissible initial data for the closed Laplacian flow. So let's think about these invariant G2 structures on this case. And let's think in terms of an overall scale and sort of the homothety class of the inherited metric. So rather than just think of these coefficient F1, F2, F3 here, then I want to think of that divided by the volume. And then if you ask that this be closed and that this homothety class be constant, then it turns out to force that G is linear and that this form is conical. So you end up getting that your Fi's are some constants times Ci's, and the closed condition imposes one condition on those coefficients. So remember, the closed condition was saying this thing here. So now you're saying C1, C2, C3, P cubed is now something quadratic. So 3 and 2 give you a 6. And so you get 6 C1. So you've got this nonlinear condition on the CIs. So you have a sort of a 2-parameter family of closed cones. So what you might wonder is, is it possible to sort of run Laplacian flow on each of those closed cones? And if so, what do I get out of it? You might also notice that, again, suppose, so if I've got this condition here, then assuming this is not 0, then all of these CIs are non-zero. So let's make a sign assumption that they're all positive. So now I've got some positive triple. This thing scales like it's homogeneous degree 3, this is homogeneous degree 2. So if you start with any positive triple, then there's some unique choice of scaling, rescaling to satisfy that. So if you think of it now, then if you fix the sort of homothety class of metric on sigma, then there is some kind of cone angle, a unique choice of cone angle that actually makes it a closed cone. So you need to write down what the soliton conditions do. So we've got the 3 form and the metric. We assume also that the vector field, we assume that the vector field is invariant as well. So it's just given by some function u. And then we're going to get some ODE system for the F's and the U's, which when you first look at it is second order in these, first order in U, and has a bunch of constraints and looks a bit of a mess. But it's possible to to rewrite it in a nicer way so that in the end, what you get is a first order system in 5 variables, where the 5 natural variables are these 3 coefficients f1, f2, f3, and then these this is a closed G2 structure. You can understand its torsion. Its torsion is always given by a 2 form of special algebraic type of type 14. We have a 3-dimensional space of invariant 3 forms, but only a 2-dimensional space of invariant 3 forms of type 14. So they turn out to be 2 coefficients that tell you the torsion form. So roughly, there is a first order system where the components are these 3 coefficients here, plus 2 things that tell you the torsion. And then if I know those, in fact, U is completely determined by this. So that's not obvious, but turns out to be the case. So the question then is, so we've got now this first order system in 5 variables, and a solution is a curve of those things. So this is telling us locally, at least, that for FT3 invariant solitons, there's a 4-parameter family of solutions. And for FT2 invariant things, I've got F1, F2, and then it turns out that there's only 1 component of the torsion in that case. So there's 3 variables, and so there's a 2-parameter family of solutions. And then the whole job is to try to understand which of these solutions actually extends globally. So so then the main somehow principle is that provided that these homotopy ratios, or these ratios F1 over G, F2 over G remain bounded, then as T goes infinity, then you really will be asymptotic to a closed curve. So the rough strategy is to sort of, again, divide into 3 parts. So you want to understand that this gives you sort of control in the middle, but you also want to have control near M and control near infinity. So, so you separate out control at sort of 0 and control at infinity. The 0 part turns out to be the most standard part. It follows argument that goes back mainly to Eschenberg and Wang, but has also been used in the exceptional holonomy cases by myself and other collaborators. This problem at infinity has a slightly different nature, and the answer depends on the sign of, well, it depends on whether you're steady, shrinking, or expanding. And then the most subtle part is kind of understanding the connection between geometry at one end and geometry at the other end. So maybe I should stop at that stage, since we're at the hour time now, and then if anybody wants some more details about any particular parts, then I'm happy to oblige either privately or publicly.
Thanks very much, Mark. Are there any questions?
So this Schränker from CRMB, do you know if it's unique?
Sorry, can you say it again?
I'm asking about uniqueness of the Schränker from CRMB.
So I believe that it's the unique one on lambda 2 plus of F4. I don't know. We still can't prove that, but there is sort of some compelling numerics that says among FP2 invariant things, it's the only one. There is a general principle that sort of says even on lambda 2 plus of F4, you probably have only at most finitely many solutions. But how many is less clear. And there is a form of rigidity for Laplacian shrinkers that holds certainly in this invariant case, but which I would conjecture holds more generally in the same spirit of, you know, Lu Wang, Kochvar, etc. That you know, there should be a kind of you know, backwards unique continuation type result. And in this particular case, you see a kind of ODE manifestation of that. So yeah, on lambda 2 plus of F4, it should be the unique invariant one, and you know, a soliton that's asymptotic to any of those cones should have the same symmetry as well, and so probably it's the only one, but there's still a lot that needs to be proven there. And then Spiro wanted to see the formula for it, I think. So let's where are we? Yeah, so
I see. Okay, interesting.
so it's actually simpler than the Bryant-Salomon.
Yeah.
And you know, so you can see that, so the cone that it's at, so the Bryant-Salomon cone would have all of these being a half.
Yeah.
So this is definitely, you know, a closed but not torsion-free cone. You know, the solution is, you know, this simple polynomial, and
what's the on the link of this cone? That's going to
yeah.
be, that's the flag here, right? Or is it CP?
Yeah.
Yeah. So what do we know about the induced metric on the link? Is there anything special?
Well, so I don't know really what, I mean, you know, the two things are telling you, the two coefficients that you have are now telling you a relative size of, you know, I mean, so this shrinker you can either regard as a shrinker on lambda 2 plus of X4 or on the flag. So it's easier to think about on the F4 case, because then it's just literally telling you something about the F4 base to the S2 fiber size.
Right.
And so it's telling you something about that relative to what would have happened in the Bryant-Salomon case.
I guess what I meant is, like, there's an SU3 structure on this CP3.
Yeah.
It's not nearly Kähler now, but it was
No.
half flat or something like that.
Yeah, but I mean, this tells you what that nearly Kähler structure is. But what I'm saying is basically, you know, what you'll want to know is these values C1 and C2, and then this closed cone condition now gives you one condition on that. So 6 times C1 C2 squared is C1 squared plus 2C2 squared. And so there's a one parameter family of those things. And basically it's a smooth curve. The torsion-free thing sits somewhere in the middle. And then if you remove the torsion-free thing, then it's got two components. everything on one side of the torsion-free thing appears as the asymptotic cone of an expander, a unique expander with sp2 symmetry. And then this particular cone here is on the other side of that. And conjecturally, that's the only thing, that's the only cone that can appear as the asymptotic cone of a shrinker. But why that's the only one, I don't have a satisfactory answer at the moment. I mean, we found the solution by, you can find in order to solve the problem close to the CP2 or S4, you have to do some kind of power series. And in order to do numerics, you need to do it up to some reasonable order. We have done that symbolically. I've started looking at this thing and it's sort of, oh, well, like 10 terms in this disappear if this value is this. Okay, let's see what that would tell me, and then you can see it has to be this. So I guess fundamentally the difference between the two cases is the sign of lambda doesn't make any difference when you try to understand what happens near the singular orbit. So but it does make a difference when you try to look at, you pick a closed cone at infinity and try to look at just an end that is asymptotic to that. So in our highly symmetric case, that gives us some other kind of singular ODE problem. But unlike the problem at the singular orbit, then it's a quote irregular singular value problem. So you find that there is a power theory solution to it, but the general solution is smooth but need not be analytic. And so you find that you might have to worry about different solutions with the same Taylor series at infinity.
Yes.
But now, morally speaking, then depending on the sign of lambda, then, well, in both cases, somehow morally speaking, the difference between two solutions, I mean, the two solutions that might have the same Taylor series differ by some kind of exponentials, but in one case, those are exponentially small. And so in the expander case, then there is, for instance, to a given cone, there is a 2-parameter family of expanders asymptotic to the same cone that differ by exponentially small lengths. On the other hand, if you try to look at shrinkers, then those exponential corrections would become exponentially large and would screw up that cone structure at infinity. So the difference is, so you have a 5-dimensional sort of phase space. You have a 2-dimensional space of closed cones. Each of those for expanders has a 2-dimensional space of ends. So that gives you a 4-dimensional space of kind of conical ends, asymptotic conical ends. That fills up an open subset of the phase space when you evolve it. In the shrinker case, you've got still the same dimensional set of cones, but each one now has a unique solution. So now you only have a 2-dimensional space of things. So now you're trying to connect, say, the singular value problem is like a 2-dimensional curve inside of, a 2-dimensional submanifold inside of your 4-dimensional space of solutions is trying to reach some other 2-dimensional thing at infinity. And so generically, they should only intersect finitely many times. Whereas the soliton, the expanders, is if you could find one and make a small perturbation of it, it's an open condition.
Mm.
And then
I see.
the steady ones have a completely different, they have a completely different kind of asymptotic geometry. So the cone is somehow forced to be torsion-free, but the rate at which they become asymptotic to it is then different. But I think there's something that one should really pay some serious attention to from the point of view of developing some regularity theory, etc., because they appear as a deformation of the torsion-free asymptotically conical thing. In particular, I can make point-wise the torsion as small as I like.
Mm-hmm.
So this is like in Lagrangian mean curvature flow, then Dominic and collaborators constructed a family of translators where the Lagrangian angle, the variation of the Lagrangian angle is as small as you like. So, Andre Neves had proven, if something had some kind of, maybe if it was in L2, then it had to be static. But this says it's quite subtle as to what kind of gap type thing you can have, that it can't be at the level, it can't be at a kind of pointwise level.
Mm-hmm.
So this I think is something that one should worry about, and Dominic conjectured in the Lagrangian mean curvature case that these translators could occur as finite time singularities unless you have Floer theory reasons to rule them out. And so anything for which you need Floer theory reasons to rule them out in Lagrangian mean curvature flow, I don't really see how you could, rule out the corresponding G2 thing. So
Right.
I would certainly be worried that these studies could appear as modeling finite time singularities.
But is there any geometric intuition how such singularities could look like? I mean, for Ricci flow, I mean curvature flow, you have a quite geometric picture of the degenerate neck tangent, and you blow up at the tip and get the bright soliton at the bowl. But
not really, because again, we don't have any analog of geometrization or something that we're trying to implement by the flow that guides you in the first place. So we don't really know what should the flow be trying to do to your original thing in a finite time singularity, say. Probably again, Dominic has some picture of how those things, these translators might appear in Laplacian in mean curvature flow. So that might give you some guidance here. So that there is some way in which these things really are a kind of formal analog of some things in Lagrangian mean curvature flow. That was how I originally got into thinking about these, that you could try to, so for some G2 manifolds where you have a circle action, you can try to take the quotient and get something six-dimensional. In the original G2 holonomy case, if you choose the right circle, then topologically at least you get R6, and the cones then are things where you've got a couple of planes in them, and then the asymptotically conical things are things where you smooth out those planes. So so you can think of in C3, take, R3 and e to the I pi over 3 R3. That's the union of special Lagrangian planes, and then there's the sort of most symmetric Lawler neck that smooths them out. So now if you want to get, say, an expander, then you want to move them away from being area minimizing. So you push them so that the angle condition is no longer satisfied. So you push them together a bit. Then there is an expander with maximal symmetry asymptotic to that. So so the expanders in the G2 thing are somehow a bit like that. So you started with the torsion-free solution, and then now there's a one parameter kind of on one side of the torsion-free cone. There's a family of expanders asymptotic to those cones. It's not quite as simple as that because in Lagrangian mean curvature flow, then the unions of planes is still a minimal thing. So it's still a critical point of volume. And so then in that case, you get exponentially fast convergence to the planes. Here, you really do have to move the asymptotic cone to some closed but not torsion-free thing, and then you only get holonomial decay to the cone. So they are an analog of those soliton solutions, these Lagrangian mean curvature flow solitons, but they have some different wrinkles. And the steady solitons are somehow what in that picture, the steady solitons are what happens if your initial union of planes does not intersect transversally. And instead there's a line of singularities, and then roughly the steady soliton is sort of unzipping things along a half line or something, or they're unzipped, and the bit that they're unzipping moves along that axis. I don't know how to give a picture of that in the G2 world. But,
oh, good, but at least it corresponds to some degenerate situation.
It should. I mean, in the Lagrangian mean curvature flow, it corresponds to a degenerate situation. Here, you can obtain these things as so there should be a 2-parameter family of expanders, and then if you blow those down in the right way, then you should get a steady, which should be one of those things. So the steadies appear as the blowdowns of some larger family of expanders.
Okay. I guess that's probably more than enough questions for Mark. Let's thank him again.